Well, we're now an expert at adding a strong base to a weak acid. Now let's flip the issue around and let's look at the titration of a weak base by a strong acid. That is, we're going to start with a base solution and we're going to add small increments of a strong acid. So the first thing we recognize is that before we add any of that acid to the weak base, we have an initial condition that's determined entirely by the pH of that pure weak base solution. So our initial condition then applies to our reaction of a base, and let's pick the reaction of our acetate anion because we know it's the conjugate base of our weak acid acetic acid, and that anion reacts in water to produce the OH minus plus the acetic acid molecule. And of course it's the existence of that OH minus in solution that drives the base character of this combination. Well, we know that the dissociation constant is a base equilibrium constant. We also know that because it's the conjugate base of acetic acid, we have the information to calculate that base equilibrium constant. It's simply the dissociation constant for water divided by the equilibrium constant for acetic acid. And we can do that immediately. That's 1.0 times 10 to the minus 14, the autoionization of water, divided by 1.76 times 10 to the minus 5, and that gives us 5.7 times 10 to the minus 10. Good. So we have our equation, we have our equilibrium constant, and so now we can use that equilibrium constant explicitly with the concentrations that are relevant to this reaction, and that is that the base dissociation constant is equal to the hydroxide anion concentration times the acetic acid concentration divided by the concentration of the acetate anion. That's 5.7 times 10 to the minus 10. We've just calculated that. And that gives us a hydroxide anion concentration of 7.5 times 10 to the minus 6 molar. Aha! So that's given us the initial point in our plot of pH versus the acid added to this strong base. And of course, we know that once we've calculated the hydroxide anion concentration, we can insert that directly into the autoionization of water to calculate the H3O plus concentration. So let's do that. H3O plus concentration is equal to the acid dissociation constant, 10 to the minus 14, divided by our concentration of the hydroxide anion, and that gives us 1 times 10 to the minus 14 divided by 7.5 times 10 to the minus 6, and that's equal to 1.33 times 10 to the minus 9. Okay, so we can immediately calculate the pH of that initial point on the titration curve. That's equal to minus log to the base 10 of the H3O plus concentration, and that gives us a pH of 8.88. Good. So now we know that our pH is equal to 8.88 at our starting point. All right, so then we are going to progress along this titration curve by adding small amounts of that strong acid to the original base solution. But we know something else, and this is always important to write down to remind ourselves exactly what the reaction is and what's happening when we're adding those increments of acid to that initial base. So we know that we have the acetate anion, that's the base. We know we're adding a strong acid, the H3O plus, and that reaction produces our acetic acid molecule plus water. But remember what's happening here. We put in 1 molecule of H3O plus, we remove 1 molecule of the acetate anion, and we produce 1 molecule of the acetic acid product. So one acid molecule goes in, one acetate anion comes out, and one acetic acid molecule is produced. And so as we work our way along this buffer curve, that's what's happening, because we strike the buffer region just as we did in the addition of a strong base to an acid. So let's take this key point that we have a one-to-one conversion of the acetate anion to the acetic acid molecule for each H3O plus that's added. Now, when we enter this buffer zone, we know exactly how we can calculate the pH. That's equal to pKa plus the log of the concentration of the acetate anion divided by the acid. All right, but we know something else. When we write down our reaction of the acetate going to acetic acid, when we reach the equivalence point, we know that the initial concentration of the base has to equal the concentration of the added acid. And so when we write our equilibrium expression, we have the fact that CH3COO times H3O plus divided by the concentration of CH3COOH. And because we get one acetic acid for each H3O plus that's added, and that means that H3O plus is equal to the concentration of the acetate anion, and that allows us to substitute in H3O plus for the acetate anion concentration, and we have H3O plus squared divided by the concentration of the acetic acid molecule in that solution, and that's equal to 1.8 times 10 to the minus 5. That allows us then to calculate the pH, and when we put in the appropriate numbers, we determine that the pH of this solution is equal to minus log to the base 10 of H3O plus, and that pH is equal to 2.87. That's the pH then at the equivalence point right here. That's the key transition point. And again, coming back to the word titration, it means that we've titrated out the original base that was in the solution by the addition of the acid. So that's the titration point, that's the equivalence point, and from that point on, whatever acid we add to this controls the pH simply by the addition of that H3O plus to the solution.